And it's only when we put those things together, okay, so we put the natural and the human together. Okay, so we're taking everything that we know that's going on in terms of natural dynamics, everything we know that's going on in human dynamics, we put them together, we get a remarkable reconstruction, the red line, of the dynamics that we actually see, that we actually observe. Okay, so when we put the two together, we're explaining most of the observed variation in the system. We can then take that further and unpack this in terms not only of temperature, but also of the radiant energy forcing. What's the net radiant energy forcing in watts per square meter? And we can apportion it. So you take that long-term record and you apply an analysis of variance to it. So you know you've got a certain amount of variation, you've got these things are contributing to it, you do an ANOVA and you can apportion the variance between those various sources. And what we find is that the observed natural plus human forcing at the end of the 20th century, the observed forcing was about 2.1 watts per square meter around the world. Our projected anthropogenic forcing was 2.3 watts per meter squared, and there's about a 0.2 watts per meter squared anthropogenic cooling, okay, as a result mostly of changes in the land surface. Over the 20th century, we have dramatically changed the land surface of the world, okay? Mostly cutting down forests, planting, plantations, reductions in ice cover. These, cause us to go from a dark surface to a bright surface in some instances, and that actually causes a cooling. There's also an effect due to the injection of essentially smoke particulate pollutants into the atmosphere, which also causes a cooling. So the net there's a small cooling effect which adds up onto this, and you end up with the observed thing. And you can partition it out like this. Okay, so overall, we're seeing in this case, this is converted into degrees Celsius forcing. Okay, you can see the effect, what we observe here. The greenhouse gases would suggest it should be slightly higher than that. Okay, but there's other anthropogenic effects here, which are land use changes, which bring it down. That's the natural variation, okay? No overall trend, all right? And that's what the internal variability is. So you can compare, for instance, the internal variability against the observed. There's no way that the internal variability can explain the observed. Okay, this is not just the internal dynamics going on there. There's something else going on forcing this. And even if you take out, these various uncertainties, for instance, with the anthropogenic land use effects, you still get a net anthropogenic forcing with a relatively small uncertainty associated with it. And that's the basis of really, the statements in the last assessment report that the human influence on the global climate system is clear. Okay, there is no longer a question about it. We can debate the details, okay, but there is a clear imprint of human effect on the global climate system. You can extend this exactly the same analysis sectorally. Okay, you can break it down into parts of the world. You can, for instance, look at Southern Africa there. You get exactly the same pattern. You can also split it down between the atmosphere, the oceans, and the cryosphere. You get the same, pattern emerging. All right. So that's all fairly straightforward. Then we move into this area of impact. So, say if the world gets a bit warmer, a bit wetter, I don't per se care about that. What I do care about is, can I grow food? Will diseases be more extensive? Will there be more natural disasters? The things that directly impact my life. And so there we have to get into the impacts area. And now we're going a step beyond the climate. We're going into the climate and then a whole bunch of mechanisms which lead us to impact. So we've got to put an impact model in there, and that's where things become a lot more difficult to do the attribution. In terms of climate change related impacts, we've detected them. In other words, we've shown that there are changes in things which are climate sensitive and on which we depend and are important to us in many, many places in the world. I was in the negotiation which finally led to this figure. It doesn't actually project very well here because the map behind it has disappeared completely. originally we'd combed the literature for studies which had done a detection kind of exercise and mapped them around the world and shown them exactly where it was occurred in the world. And when it went into the plenary negotiation, the countries of the world, and particularly the countries in Africa, said, no, we don't want it attributed to the actual location. You need to lump this into broad areas, because it was giving a false indication that Ghana was affected, but the Ivory Coast wasn't affected, as simply that Ghana had a study and the Ivory Coast didn't have a study, and so they generalized in this. But the point about this indication is that across many things, okay, this is the physical system, these are ecological systems, so in forests, in water systems, in marine systems, in human and managed systems, croplands, livelihoods, across many axes and across everywhere in the world, we are detecting the impacts of climate change. We're detecting the impacts of, we are detecting the effects of climate change. We have not been able to attribute those in many instances to anthropogenic climate change. Okay, that's the additional step, which is much more difficult. But these are climate influenced change which have statistically changed over the period of observation. So the issue is that the longer and more complex the causal chain is, the harder it is to do attribution. This is not a unique problem to climate change. It is, for instance, a problem which is very familiar to you if you've ever worked in the area of technology attribution. Okay, so we're all kind of in the business of saying, well, this research that we did at institution XYZ, it changed so many people's lives in this way. Proving that is actually damn difficult. Okay, firstly because changes in people's lives usually have multiple causes. There's not usually a single actor. They're contingent, they're dependent on other things going on, and they often take a very long time to come through. So it's a difficult thing to do, precisely because of the fact you've got this multiple causal pathways and long causal pathways, which this has to change, then that has to change, and it takes time to go through the system. So those are some examples of attribution studies which have been done in this impacts area. So it's not true that nothing is attributable. Some things have been attributable to anthropogenic climate change, not just climate change, okay? But the process of doing this is a long and difficult process. And the standards which are set before we come out and say, no, that one there, that was anthropogenic climate change, it's a very high bar that you have to cross. And so that brings me on to a question which I get several times a year. Whenever there is a dramatic climate effect somewhere in South Africa, my phone starts ringing off the hook, okay? Is this, proof of climate change? Here's a great example, that tornado which occurred in Gauteng just a couple of months ago. Now, I've grown up in Gauteng, I've spent my whole life here. I've never recalled a tornado. I actually started my scientific career as a tornado chaser in Oklahoma. I know what a tornado looks like, okay? We just didn't have them. But over the last couple of years, if you've been paying attention, to the sort of, third or fourth page in the newspaper, you'll suddenly see, a severe windstorm blew off a roof in the Transkei, or, suddenly these things are starting to appear of severe storms. So at what point do you say, that is anthropogenic climate change, rather than just a rare, severe event which occurs every now and then? So by definition, severe weather events are rare. Okay, if they were common, we would just, well, that's just the way it is. For instance, let's take an absurd example. It makes a dramatic difference to us when the sun goes down. Suddenly the lights go out. It gets cold. If that didn't happen every day, okay, there would be, a great deal of public outcry if someone suddenly turned the lights out. Or, for instance, in, pre-scientific times when we had an eclipse, okay, suddenly this was an unheard of thing. But the fact that it happens every night means we've totally internalized that. We've become used to it. And it's very similar with severe weather events. So the things that we regard as shocking and severe are the things which, by definition, only occur once every 20 years or every 50 years or every 100 years. Now, the statistical problem that comes in is if you're trying to detect a change in frequency of a rare event, you need a very long run. So let's say this was a 1 in 50-year event. How long a run of observations would you need to statistically, hand on the heart, okay, say, that was a change in the statistical frequency, okay? You would need a run of several hundred years. We don't have weather records in the country running several hundred years. A related problem is the problem of severe tropical storms, cyclones. So lots of us, sort of looking around the world and saying, haven't these things picked up a little bit? Why is the eastern seaboard of the United States getting clopped every second year? And the Philippines recorded the highest wind speed that they've ever recorded until the anemometer blew off its axis, etc., etc. Surely we must be able to prove this because we now have global satellite coverage. We're picking up every one, but we've only had that kind of coverage going back until the 1980s. Before that, all we have is subjective records of storm severity, the sort of Beaufort scale. Yes, that was a big storm. Okay, all right. So you've got to troll back in the Mariner's records and say how many, yes, that was a big storms were there versus, we had severe rainfall. And that's, intrinsically a difficult thing to do. So I have no doubt that we will see very conclusive understanding of changes in severe storm frequency going forward, now that we have a global observation system which can consistently measure the severity of severe storms, not just from wind speeds, but actually from the total energy in the kinetic energy in the storm, and we are starting to see changes appearing in that. One of the interesting things is that what seems to be changing more than the frequency is in fact the amount of energy encapsulated in a particular storm. And that's totally consistent with our understanding of how greenhouse gases affect the energetics of the environment, of the atmosphere. Basically, as I like to explain it to my mother, we're putting the climate system on steroids. We're just, oomping everything up. We're pushing the temperature up, that's pushing up the water content, we're pushing up the amount of energy that's in circulation. We would expect this to manifest in severe storms, not necessarily more severe storms, but storms, not necessarily more storms overall, but a greater number in that severe category. All right, so given that climate, by definition, is a statistical concept, the climate is the average of the weathers. So weathers are individual events, okay? Climate is what happens, to weather over time. It's the statistical concept. You then can't, then take an individual event and say that's a change in the climate, okay? Because we're actually talking at two different scales. The one's a statistical concept and the other one is an event context. But there are things that we can say. If you get a sequence of events, okay, which statistically are outside the range of what you've established, then you can say that something has changed there, okay? Or even if you have an individual event which is so far outside the prediction envelope, okay, you then have strong inferential reasons to say that something has changed. Are we yet there with severe storms in South Africa? I don't know, actually. We must be getting quite close. Certainly our insurance claims are saying that something has dramatically changed. Now the problem with that is, of course, is that there's more of us, okay? And we've built more buildings and we've put them in harm's way. So you have to take out that underlying, driver and try to normalize for that. But if you were in the short-term insurance business, you would certainly, and they are certainly, paying attention to the fact that we now have increased storm severities. And so you get things like Discovery Health getting into the weather radar business and sending you SMSs when it's about to have a hailstorm in Johannesburg. That last big hailstorm in Johannesburg of about 3 years ago. That was about I think it was an 800 million rand event. Okay, so these things have enormous consequences, and understanding what the trends on them are really important. The other event which is sort of fresh in people's mind is the 2-year drought event that we've just emerged from, which was associated with an El Nino 2015 to 2016. Two big consequences, big failures in agriculture. Any of you who've been to the supermarket recently and tried to buy meat will find it's costing you twice as much as it did 2 years ago. That's because the national herd got decimated, and now farmers are rebuilding their herd and not putting them on the market. Okay, so the price of meat has gone up dramatically. So big impact on through drought. Also a big impact through elevated temperatures, heat waves, high temperature events. And as South Africans, we like to think that we're really rugged. That big event which occurred in Paris of, what was it, about 10 years ago, where approximately 40,000 people died, okay, prematurely. So you can say, well, they were old, they were going to die anyway, Well, I see quite a lot of gray hairs, in this room, does that bring you comfort? Okay. So the point is that when you have these heat wave events, and that was an elevation of temperature of about 10 degrees over the norm, maintained for nearly 2 weeks. That's what brings on your mortality. It's not 1 day of heat. It's a protracted period of substantially high warmth. And it takes out the vulnerable people in society. So it is the elderly, okay, and it is the very young, and it's the people with various health compromises, people with, respiratory problems, etc. But we like to think, please, those were Parisians. They can't handle the heat. I'm a South African. I can take the heat. So it's a very interesting question about physiologically whether in fact we're different. And we have some interesting results out of animal studies. So there is a wonderful group in the medical school at Wits who studies high temperature metabolism of mammals. And they have revolutionized this area largely by, previously, many of you might have read all that stuff about how does the gemsbok, survive in the Kalahari. Oh, well, it's got this, long nose with all this temperature exchange mechanism in the nose, which cools the air as it's coming in and exchanges it with the hot air, so its body might get warm, but its brain stays cool, and, and its testes stay cool as well because it puts them on a spring, all of that sort of stuff. It actually turns out to be rubbish. And we've revolutionized that by having implantable temperature loggers. So previously what you did to do a study like that is you went out there and you shot an eland, or you shot a gemsbok, and then you rushed up to him quickly and you stuck a temperature up its bum, okay, and got what is core temperature. Turns out that's completely unrepresentative of the body temperature. Whereas if you actually surgically implant a little tiny monitor and you let the thing wander around doing its business, for a year, and then you go and you pull it out again and unpack that, you find that across the whole class of mammals, and I would point out that we are mammals too, there is hardly any variation in body temperature. You, your dog, in fact your budgie, everything falls within a very narrow range.